Next, I want to talk about some of the other thermodynamic relations that are introduced in this chapter. I am not really going to spend much time on these, but I just feel like it's unfair to throw you to the wolves and say, well, one day you may run into this variable, but I'm not going to have talked about it. So, there are a couple of things here. First of these is the Helmholtz energy. Now, most textbooks use A as the symbol for Helmholtz, which I know seems strange since it is not in the word anywhere. But A is a typical symbol used for the Helmholtz energy. Your book uses a psi for the Helmholtz energy. But it is somehow like, if you'll recall, we had U plus PV was the relationship between H and U. Well, this is a similar relationship that shows up in certain applications, and it's the Helmholtz energy, and it's U minus Ts. So it's, again, just a variation on the energy. But the Helmholtz energy in certain applications is a more natural equation set to work with. It will give you simpler looking equations. Another one of these is the Gibbs energy, which is H minus Ts. Now, the Gibbs energy is particularly useful when we start talking about phase equilibrium. So when we talk about how you have that vaporization happening and you have stuff happening in two phases, a liquid and a vapor, Gibbs energy is going to be the variable that's going to be most convenient to describe mathematically what's happening. Now, for a simple pure substance, it's not really complicated enough to justify going into the Gibbs energy. But when we start talking about mixtures, where the material will separate itself into different compositions in the liquid and the vapor phase, for instance, I can describe that relationship most easily using Gibbs energy. So Gibbs energy is enthalpy minus Ts. For our purposes, it's just another form of energy, and we will come back to this in a later chapter. These next several are variables that relate pressure, volume, and temperature to things that are occasionally a really handy way of describing a process. So, for instance, if I have something where it's a constant pressure process, but I have the temperature changing, the volume will probably change. If I wanted to predict that, I might want to quantify it as a volumetric expansivity. Beta is the symbol most often used for this, and it's 1 over the specific volume, or sometimes this is the density, and how volume changes with temperature while holding pressure constant. And one of the main reasons I want to talk about these variables at all is because when you see them, the thermodynamic notation, we put a subscript on a partial derivative to indicate that that variable is being held constant. Because remember, in thermodynamics, we have so many variables. And so if I want to have a very well-defined system, it is helpful to be very explicit about what is being held constant. So in an isobaric process, one with constant pressure, how does volume change with temperature? Beta, or the volumetric expansivity, describes that. I also have isothermal compressibility. So this is for a constant temperature process. If I change the pressure, how does volume change? We can see that beta and kappa are going to give me similar stories, but one's going to tell me the temperature change component, one will tell me explicitly the pressure change component. So together they give me a much more clear explanation of what's happening to volume through a process. I also have an isentropic compressibility. This one isn't used quite as often. Alpha is the symbol used here. It's not the same as the alpha used in, say, a heat transfer course. So be a little bit cautious with this one. But this is a constant entropy process. Remember, we run into those if we have something that we say is reversible and adiabatic. One last one that's very useful is the Joule-Thomson Coefficient. This is very handy when you are talking about expansion valves, such as we used in a refrigerator. These are those devices that allow me to drop the pressure with a very simple piece of equipment. And what this is it says that if I go through a Joule-Thomson valve or an expansion valve, then H is approximately constant, and so as the pressure changes, what will happen to the temperature? So if I know this Joule-Thomson coefficient for a substance, then I'm able to more quickly and efficiently predict what's going to happen as it goes through this valve. So again, this is just an introduction to some other variables that you may run into. The Joule-Thomson coefficient, again, refrigeration. This is a way that people describe the expansion valve. Gibbs energy, we are in particular going to come back to this when we look at phase change for multiple component systems.